Good evening, everyone, and welcome to our next video series for College Prep Algebra 2. This is the second half of Unit 2. We're picking up here right after the semester exams, and I will try to have a video up for nearly every lesson if I can from here on out. So we're starting here where we left off in um, our polynomial unit. We just finished a big unit on the properties of polynomials, the properties of the long division, and how intercepts and factors and everything ties together. The second part of this unit, now that we're past the exams and starting fresh again for the third quarter, we're going to be looking at these things called rational functions. And this is a pretty interesting unit. I'm going to try to keep these videos as short as possible, trying to split them up so I'm not making 3-hour videos. So we'll see how it goes. I'm also using some brand new software. I'm using OBS Studio to make these videos. It's basically the same stuff that Twitch streamers use, so this ought to be kind of interesting, but it looks like it's pretty full of features. Okay, with that out of the way, still using good old Smart Notebook though to present the slides to you, just like we would do in class. So for those of you watching these videos for the first time, what you're in for is just a lesson that's going to be pretty much what we do in class, uh, but without all the little distractions that can happen in class. I'm just going to go through all the different slides, and this is for you to use at your leisure for studying, for reviewing, for watching while you're absent, whatever the case may be. So hopefully I fixed some of the volume problems on here. That was my main motivation for downloading this software. Some of you had said that my voice had come through kind of quiet, and I had some ways to kind of toy with that. So here we go. Okay, so the first lesson that we're going to look at is lesson 17. This is just an introduction into what a rational function is. Okay, so first, a rational function. What is the base word for the word rational? Well, if you might guess, it's the word ratio. And so we're going to highlight the word ratio here. And so when you think of ratio, what do you think of? Maybe a fraction. A ratio means something like this number to this number, or maybe like 3 to 5, 3 divided by 5. Anytime we use division, that creates something that is rational. And that means that a rational function is a function that involves the division of two different expressions. Generally, we can simplify and say the division of two polynomials. So a rational function looks a little bit like this. Rational equals, we like to abbreviate it like this. P of x divided by q of x. And so what those are referred to are polynomials. And so it's one polynomial divided by another polynomial. Now, sometimes those polynomials are big and long, sometimes they're not. They could even be single numbers. Remember from our previous work, even a monomial or even a single number like a 1, like 1 is considered a polynomial. So just keep that in mind as we go through here. So here's a little bit of some vocabulary. We're going to look at something called a vertical asymptote. Oh, what is this word? Okay, asymptote. All right. Well, we'll have a definition for that in a bit. And so this main lesson is identifying and introducing some of the concepts that you'll see going forward, not just in this unit, but things you'll see for the rest of the course, and also when you go on to pre-calc and calculus as well. Okay, so let's start with a bit of a warm-up to kind of introduce how this unit is going to go. So let's say we have an aunt, or Jack does anyway, and Jack's aunt plans to bike 10 miles. Okay, so you ever get on a bike? You like to ride? Wonderful, right? I do like to bike when I can. And when I think about it, I have a daughter, and I ride with her, I ride slow, it takes us a while to go around a loop. But if I'm biking by myself, I might bike faster, and then it takes me less time. That's the sort of thing that we're going to see a lot in this unit. So let's answer some questions. How long will it take if she bikes an average rate of 8 miles per hour? Okay, so she bikes 10 miles, right? So 8 miles per hour. So 8 miles per hour for 10 miles, okay? So if we think about this, how long will it take? Well, do we have any sort of relationship here that we can use? Well, you might be familiar with the equation distance equals rate times time. D equals RT. Maybe if you've taken science or physics, you might have seen that equation. So that's kind of the way that we have to deal with this. So 10 miles, and she goes 8 miles per hour. So wouldn't we just then say that we would take the 10 and divide by 8, so 10 miles, divided by 8 miles per hour. So we can think about this because of the question of how long, right? So we want to solve for t. How long will it take? So if I want to solve for t, then what I would do is I would divide both sides by r, and I would end up with the equation t equals d divided by r. And that's what I did here. So I took the distance and divided by r, which is the rate. So in this case, I do 10 divided by 8. Now, 10 divided by 8 is 1.25. 1.25 hours. Okay, how long will it take if she bikes at an average of r miles per hour? Okay. Well, same kind of thing, right? But instead of using 8, we're using r. So can I just replace the 8 with an r? Sure, why not? Let's just do that. And we will say that distance equals, or sorry, not distance, I'm sorry, um, time is equal to 10 miles divided by r, or 10 divided by r. And that's going to be in terms of hours. Now, you may be wondering why that turns into hours. Well, as a side note, this is why it turns into hours. If you take miles and you divide it by miles per hour, okay? Do you remember the rule for dividing a fraction? When you divide a fraction, it's the same as multiplying by the reciprocal. So this is going to equal miles times hours over miles. And the miles cancel out, and you're left with just hours. So it does work. So we are left with 10 over our hours in that case. So while this may be, kind of the technical explanation, you might be more apt to kind of think about this over here, the distance equals rate times time. If you just simply know that, you can always, plug in the values that you know. You can plug in the 10, you can plug in the 8, and you can solve for t. Okay? So you can kind of do that for any of these problems, right? Okay, Jack wants to join his aunt, but he only has 45 minutes to exercise. What will the average rate need to be for him to finish on time? Okay, so he only has 45 minutes. So they want to bike for 10 miles, right? So the goal is to finish on time, which means they have to do the whole 10 miles. Okay? But they only have 45 minutes. So if we think about the formula again, let's do it kind of using the formula this time. So D equals R times T. Now, in this particular case, what do we need? We need the average rate. So we need to solve for t, or sorry, solve for r in this case. But let's plug everything in, right? We have, how much distance do we have? Well, it's still the same 10 miles, right? We're solving for r. Now, what's t in this case? Is t 45? Ooh, careful, not quite. T is not 45 because t is in hours. How do we know it's in hours? Because our rate was referred to as miles per hour. So we're going to say that t is an hour. So now, could you use 45 for t? You can, but what you would get is you would get a rate of miles per minute. But don't we better understand miles per hour? So I'm going to put in 3/4. And that's because 45 minutes is equal to 3/4 of an hour. Hopefully, um, you can logically see that. So all we have to do is solve for r. Okay, so we solve for r. Now remember, if I need to solve this equation for r, multiply by 4/3. And so what I get is I do 4/3 on the other side. And I get r equals 40/3, which is, 13.3 miles per hour. So that means that Jack and his aunt need to average 13.3 miles per hour in order to get the 10 miles done in 45 minutes. So now let's generalize this. What will their average rate need to be if they have t hours to exercise? Okay, so t hours to exercise. Well, same thing, right? If you notice what I did, I'm solving for r. So if I take this equation and I solve it for r, I get r equals d over t. So the rate that they need to travel is 10 divided by t hours. And that's exactly how I did the calculation for number 3. The idea behind all of this is division. These functions involve dividing by some sort of variable concept. And one of the big things that's going to come out of this is what I said at the beginning, that in a case like this, the less time I have to exercise, the faster I need to go. So, and the same thing for above. The faster I go, the less time it takes. When you have division of some sort of variable concept like this, when one piece increases, the other decreases. So if we're dividing by a bigger and bigger number, it's going to cause the rate to go down, despite the fact that time is going up. That's a big piece of dealing with what we call these rational functions. Okay, so let's look at this now and what this might be as a graph, because now that we've kind of pieced together some of the thinking here, let's see what this looks like. So write an equation that gives his time t in hours as a function of his rate r in miles per hour. So remember, he's biking 10 miles, right? And as a function of his rate. So remember that we solved for t earlier, right? And we said that t was equal to distance divided by rate. And so since we already know the distance is 10 miles, we can say 10 divided by r. So t of r is equal to 10 divided by r. I just plugged the 10 in for d. Okay, so once we have that, let's label some axes, right? All right, let's scroll down here. So graph y equals t of r, label the axes. So let's label, right? So down here, what is the x-axis going to represent? My independent variable, rate, in miles per hour. And then what will this represent? Time in hours. So how long they're going to take. Okay, so let's plot a few values, right? So what if he goes 1 mile per hour? What if he goes 1 mile per hour? Okay, 10 divided by 1 is 10, right? If he goes at 1 mile per hour and he needs to go 10 miles, it makes sense that that's going to take him 10 hours to do that. Now, I can walk faster than that. I think you could too. Okay, how about 2? So 2, well, 10 divided by 2 is 5. Likewise, you can logically think that if you're going 10 miles and you're going 2 miles per hour, that's going to take you 5 hours to do. And so we can continue this pattern and just basically taking these numbers and dividing them into 10. So 3, well, this one will be a decimal because you'd have to go a little over 3 hours. 10 divided by 3 is about 3 and a third. 10 divided by 4 is 2.5. 10 divided by 5 is 2. 10 divided by 8 is 1.25. 10 divided by 10 is 1. 10 divided by 15 is just under 1. Because if you're going 15 miles per hour and you have to only go 10 miles, you can do that in 2/3 of an hour. So here's the function that you end up with. So I'm going to try my best to draw a sketch like wee through all the points. Here we go. I kind of missed a little bit on the end there. Let's see if I can fix that. And do that. Oh, that's a little bit better. Okay, I'll call it done. All right. So, what is the meaning of T of 8? Well, we've already covered that, right? So, we have decided, we know that T of 8 is going to be 1.25. It's going to be 10 divided by 8. So, what does that mean? It means that at 8 miles per hour, Jack takes 1.25 hours to go the 10 miles. And we can do that for any of these numbers. But now we have some interesting questions I could ask from this. Notice the way I did this, and notice I started my graph at 1. Why couldn't I start at 0? What is T of 0? Well, he's going 0 miles per hour, right? So 10 divided by 0 equals, well, wait a second. If he's going 0 miles per hour, what's happening? He stopped. He's not moving. If he's not moving, is he ever going to go 10 miles? No, he is not. So guess what? We say that this, we'll erase this here. It's not really question marks. This is undefined because it does not have a physical value. We don't know how long it's going to take because he's never going to make the 10 miles. Now, likewise, we could do the same on the other end. Okay, what's going to happen the faster he goes? The faster that he goes here, what's going to happen? The faster he goes, well, he's going to take less and less time, right? We could say he travels 15, 30, 50, 60, 70 miles an hour. It's pretty fast on a bike. I mean, could he theoretically travel 340 miles an hour? Sure. How much time will it take? A very small amount of time. But will it ever time? Notice this. Notice this graph is getting closer and closer to the axis. Here's my question. Will this graph ever reach 0? The answer, no. Same reason, right? The time's going to get faster and faster, but we're going to think about it in a different situation this time. If he's traveling faster and faster, it still takes time, no matter how fast he goes. Some time is going to elapse to get from point A to point B, even at the speed of light. Even though light is like the fastest thing in the universe, it still takes time, just a very small amount of time, to travel 10 miles. So here's an interesting case that kind of is a different function than the functions that we dealt with last unit. We spent a lot of time last unit looking at the idea of intercept. So function crosses this axis, function crosses that axis. These functions have an unusual behavior in that they don't cross the axis ever. They look like they're going to, but they never do. This concept here and here, these are called asymptotes. Here and here. So we'll come up with a formal definition of that in just a bit, but it's the idea that a function, is going to increase, one part of a function will increase a lot, which will cause either the input or the output to get really, really close to zero or some other value, but never actually reach there. So we're going to explore that over the next few days and a few lessons. Okay. All right, so these questions are basically just the ones that we just kind of talked about. As r gets closer to 0, and what is the meaning of t of 0? We've talked about t of 0. Does this value make sense? No, right? So let's fill this in. So now that we've done this, we know that 10 divided by 0 is undefined. And so why was that? The reasoning behind that was that 0 miles per hour means we never get to the end. But now the next piece that we have to look at is not just what's happening at 0, and we've talked about that, but what's happening near 0. Okay, so in this particular case, let's think about this. Now, 0, clearly we can't do that. But what if he's just going really, really slow? So at 1 mile per hour, it's going to take him 10 hours, right? Well, is there a point where he goes slower and slower and look how it's going upwards? What happens when he goes half a mile per hour? 1/10 of a mile per hour, it's going to take him 100 hours. At some point, it's going to take a week or even a year. He could go slow enough that it takes him a year to do this. So near 0 miles per hour, very slow. Very slow means long time. Oops. Sorry, long time. Oh, I could have left that, I suppose, just to be funny, but a long time to go 10 miles. And so the slower he goes, the longer it's going to take. And the same thing's true on the other end, right? So faster and faster means that time is smaller and smaller. But as we said before, it's never going to get to 0. It's just going to take a very small amount of time, even at the speed of light. Okay, so let's kind of define these now. So first off, a rational function. A rational function is a function that's defined by a fraction with polynomials in the numerator and denominator. Now, rational functions include polynomials. Um, Polynomials can be written as a fraction with a denominator of 1. Remember, numbers like this are considered polynomials as well. So if we go back here, this expression 10 divided by r, this is a rational function because r by itself is a polynomial and so is the number 10. They just have a very low degree because they don't have exponents. So r has a degree of 1 because it's a linear, r to the first, and 10 has a degree of 0 because it doesn't even have a variable. But they are considered polynomials, so this is considered a rational function. Generally speaking, though, we consider rational functions, like when we think of a function as a rational function, we consider the cases where there are variables in the denominator. So even though that, yes, you could have a function like, I could have a function like this, like f of x equals 2x plus 3 over 5. That is technically a rational function, but because there's no variable in the denominator, this is not going to behave any differently than, say, a linear function. This is, a line. But in this unit, we're going to be concerned with functions that are maybe the other way. So functions like this, maybe I have x plus 3 over 2x minus 1, or 5 over x plus 7. Those kinds of functions, because they have special behaviors that happen, when x reaches certain numbers. And that's where we get into something called the vertical asymptote. The line x equals a is a vertical asymptote for a function if the function is undefined at x equals a and its outputs get larger and larger in some direction when x gets closer and closer to a on each side of the line. So here are the keywords here. Larger and larger, the outputs get larger and larger, closer and closer to a. Means the graph goes off in the vertical direction on either side of the line. Kind of like this. So this is what was happening, but it happened on the axis itself with the last function. Notice this graph, it's going along, then all of a sudden it shoots up. And it just kind of skirts along the A line here and never actually crosses it. And on the other side of A, the function goes and comes down again, but never actually crosses it. So it's almost like the function teleports to the other side of the line. Now, functions can't really teleport, just the same as you and I can't. But the idea here is that this graph does not actually have a point that's directly on the dotted line. Same thing here. No point directly on the dotted line, although the function comes really, really close as you want to that line. Close, but never actually touches it. And the reason why it never touches it is because at that line, there is a division by 0. And that's why it's not defined. So that dotted line represents the location where in the function something gets divided by 0. Because we know that's the one limitation of division is you can't divide by 0. Everything else is good though. That is what's creating these asymptotes. So let's look at these functions. Okay, so here, f and g are both rational functions. Functions are defined by f of x equals 6 over x, and g of x is 6 over x minus 1. Here are their graphs. Okay, so let's think about the similarities and differences. Okay, so if you look at these functions, what's the same about them? Well, they look pretty much the same, right? Same kind of curve, almost the same location, almost the same points. But let's look at some locations. Say, what's a good point to look at? If we look at, say, this point here. Okay. So this point here seems to be 2, 6. And we have a point down here. Maybe this one seems to be 4, 2. And you can plug them in and you could show that that's certainly true. Over here, we could do much the same thing over here. This point over here is -2, -2. But I want you to think about this. Look at where this dotted line is. Why is there a dotted line here? And why is it at 1? Okay, so if we look at this, this dotted line, the points along this dotted line are located at 1, something. Okay, well, here's what happens. Let's look at this function down here. Try plugging 1 into this function, and you will get 6 over 1 minus 1, 6 over 0, which is nothing. Okay, and that's why that dotted line is there, because we can't divide by 0. Well, how does that play into the other function? Well, same thing, right? Now, what value of x in this case is going to make that dotted line? Well, it looks like x has to be 0. Because, well, if I plug 0 in, 6 over 0, again, nothing. And in this case, that's where the dotted line sits. The dotted line sits at 0. Because for this function, plugging 0 in for x causes bad things to happen. So that's the main difference between these. And you're starting maybe to get a sense of, how to find these vertical asymptotes. Okay. So, a couple things. So let's look at these activities, right? Ooh, card sort. With a partner, match the graph to the rational function that it represents. Okay. Well, I have a partner. My partner is me. Yay. So it's me, myself, and I all working together in a group. Okay, so let's take a look. So it would appear that the biggest difference between these functions, right, is having to do with where these asymptotes are. Okay, and so let's try to figure out a few of them. All right, let's look at the difference between the cards. Well, we have, looks like graph F and H both have a dotted line at -2. Okay. B and D have asymptotes at 0. Okay, dotted line at 0. Graph E has a dotted line at 2. Okay, so that one's by itself. Okay. Okay, so is there any function up here? Remember, those dotted lines seem to happen when we divide by 0. So which one of these functions up here can I use that if I plugged +2 in for x would cause a division by 0? Looks like it's gonna be, this one right here. So if I plug 2 in for x, I'm gonna get 2 minus 2 is 0. So I would say, I'm gonna say 1 over x minus 2. And that's because I have a vertical asymptote at x equals 2. Hey, doesn't this seem a little bit now familiar to what we did with intercepts and factors? How we had to solve, and if we saw x minus 2, we wrote down +2. And that was an intercept or a solution. Well, guess what? That same process determines vertical asymptotes. So if we have a function that in the denominator has a polynomial in it, then its intercepts or its solutions will form vertical asymptotes. Wonderful. Okay. Hey, that means we can start matching these up pretty easily. Oh, well, some of these, we have two with the same asymptotes. But anyway, so let's look. Let's look at these x's, right? So graph B and graph D, both of those have a vertical line at 0, which means they have a vertical asymptote at 0. The functions that are going to do that are going to be p of x and r of x. So now the question that we're going to ask ourselves is, how do we figure out which one is which? Oh, wait a second. Oh, positive, negative, right? Wait a second. Look at these functions. Both functions have a positive piece and a negative piece. How do we determine which one's which? And it's not even the function kind of which one of them looks like it's going up, down, like positive, negative. They're just mirror images. So how do we figure it out? Same way we'd figure the rest of it out. To separate these, maybe let's pick a point. Let's look at graph B. Give me a point that's on this function. Right here. Looks like that point is 1, 1. Okay? So, which one of these functions can I plug 1 into, my input of 1, that I would get an output of positive 1? Is it going to be 1 over x or negative 1 over x? Well, let's see. This one, if I plug 1 in for x, 1 over 1, that's positive 1. Well, looks like this one's p of x. This one is the positive 1 over x. Doesn't look very positive, does it? Well, I guess it's in the first quadrant. Positive, positive. But what about these points here? How then would these points work? Well, let's think about it. Let's pick a point here. Let's pick the opposite point. Negative 1, negative 1. What would I get if I plugged negative 1 in for x? Well, 1 divided by negative 1 is negative 1. It works. Likewise, that means this one must be negative 1 over x. Well, does that work? Let's check a point. Let's do this point down here. This point is 1 comma negative 1. Okay, so once again, input. Let's input 1 in for x. Negative 1 over 1 is negative 1. So it works. And if I input negative 1 divided by negative 1 is positive 1. So that point works as well. Let's use the same logic for the others. So now we know that F and H, T and Q, this one's got to be T or Q. All right, let's pick a point. So maybe this point here, this point looks like it's going to be negative 3, 1. So which point could I do that? Well, I'll get an answer of 1. Well, let's start with this one. 1 over x plus 2. So I would get 1 over negative 3 plus 2. Well, that would be 1 over negative 1. That's negative 1. Oh, not that one. This one's got the negative. It's going to cause that sign change. It's going to turn that to a positive 1. So guess what? This one's Q. And this one must be T. And you can prove it. Here, you prove it by plugging in this point right here. This particular point is um, negative 1, 1. And if you plug that in, you would get negative. Now, negative 1 plus 2 is 1. Uh, so negative 1 plus 2 is 1. 1 divided by 1. Oh, not t. Oh, I got that backwards. Q, t. Oh, they're written backwards. I meant that this is q. Okay. And then that one's t. I did get that backwards, didn't I? Okay. Whoopsie. Okay. No, I had that right. I was reading the wrong function. Okay. Never mind. I had the wrong function there. Okay. That one is t. Okay. So in this case, 1 over negative 1 plus 2. Negative 1 plus 2 is 1, and 1 divided by 1 is 1. So it works. Okay. Sorry about that. It just had a little bit of a skip there. So this one would have to be negative. Okay. So we matched it up. We have Q, P, T, and then R, and then graph E. Looks like that one was V. Okay. And so that covers that. So we can tell a lot from the asymptotes, from locating where those asymptotes are. But then after that, we may have to do a little bit of a check just to see which way the orientation goes. Okay, so real quick, a little bit of summary here, how to find a vertical asymptote. A vertical asymptote is a line that the curve approaches but does not cross. Completely ignore the numerator. Only the denominator matters. Okay. All you have to do is set the denominator equal to 0. Vertical asymptotes can only occur when the denominator is 0. Division by 0, result graph avoids that. And yes, there can be more than one vertical asymptote for a rational function if there's more than one variable value that makes the denominator 0. Okay, so let's super quick here. Let's determine the vertical asymptote for these functions. Okay, so when I look at this, just remember that the goal here is to make the denominator equal to 0. And hopefully should not be any much concern. Remember, the numerator, top of the fraction, does not matter. So the vertical asymptote, and we always write it as x equals. Vertical asymptotes are always written x equals because you're solving for x. So in this case, x equals 5. Vertical asymptote, negative 7. Now, keep in mind, the negative 7 is what makes this denominator equal to 0. This negative on the front, again, that does not matter. That does not impact it. It could be in the numerator, could be elsewhere, does not matter. All that will do is it will flip the function. But when you flip the function up and down, what's going to happen is the avoiding spots are still going to be in the same place. 12 over 0 is the same thing as negative 12 over 0. Negative won't change anything. What about number 3? X equals 1. Again, the numerator does not matter. So the fact that negative 1, the fact that you have a negative 1 would make the numerator equal to 0 doesn't matter. That just means that the function is 0 at that point. Actually, in that case, that would cross the x-axis. So this particular function is unique in that it has an asymptote and it crosses the x-axis. Okay. How about this one? Now, this one's got 2 factors in the bottom. And so it will have a vertical asymptote at x equals negative 2 and x equals positive 4. So it will cross, it'll actually cross the x-axis twice, which is interesting to note, and it will not only do that, but it will also have two asymptotes. And if you'd like to see that on a graph, I can quickly show you what that will look like. I'm not sure if I can do that now. I know my computer is locked up recording, so um, maybe I'll have to show you that one in class. All right, I'll have to figure out how to get that to work if it will. Oh, wait, there we go. Here we go. And if I do that and I do that, and here's Desmos. Got it. Okay, so that function was x squared minus 9 divided by, and it was, let me bring that up again. What was that function? It was x plus 2, x minus 4. Whoa, look at that function. So here's a really unique function. Now, Desmos won't show you where the asymptotes actually are. They're not going to draw the dotted lines for you. But you can kind of see where they would be. And you can kind of see how they would be at -2 and how they'd be at 4. And I can kind of do that here. I can do x equals -2, x equals 4. And there you go. You can kind of see where those intercepts are. Now, this is a funky looking function with 3 separate portions, isn't it? But that's what these functions do. And we can describe some of the values and properties as we go along. All right. So there's our first lesson on vertical asymptotes. If you have any questions, feel free to let me know. Have yourselves a lovely evening, folks. Take care.